maybe you have a second project, and maybe that project is on the high efficiency and resolution Mercator Echelle spectrograph, or Hermes, and you have a night of data that you have to analyze, and you have no idea what to do. Welcome to the club. If you, help somebody else out and make a video that's better than mine, it'll go a long way. But hopefully you're a Python pro, and I'm going to walk through my Python program, and then hit some points on the report, and then show you one of the executions of a file that you've got to learn how to use. So Python, import your libraries, and open your files. So download all your files. Some scpr command. Look more on that in the report. Make your plots. Plots are in the report. Hang on. And the first thing you'll try to calculate is your Blaze wavelengths, which is the peaks of your calibration file, or something like that. And then you'll get Blaze angles, and they should all be about 70. And then you can check for errors. I don't think that's required, but it's one of the few things I know how to do, so I actually did it because it was easy for me. Only thing easy for me. And then resolution sampling is sort of how wide your, how many pixels your detector needs in order to capture a signal. So obviously if you have two things next to each other and they're like blasting overlapping pixels, then it's not very, good. You're not going to be able to see that it's actually two things apart from each other on the sky. And so you want, everything in the whole universe to come into your detector on one pixel and not its neighbor. But that never happens, and so the ability for you to minimize the number of pixels that your signal comes spread out on is its resolution. And you can try to find a Gaussian distribution over every single one of your peaks. I ran out of time and did not. And hopefully you're, well more Python savvy than I am. Good luck. And, the deadline will arrive and you'll be done, whether you're finished or not. So try to get all the resolutions from all the peaks and all the orders. Hopefully your for loops work. And then stability. Stability is a program that I don't think I'll show you, but this is the command for it, and you can find more in the report. And then free spectral range. This is, I think, all the differences between the orders on wavelength. I'll show you a picture. And then efficiency is something I will show you right now. You're going to open these files up, determine their object that they're looking at, so which star in the universe, and then go to Vizier or Simbad. I'm not going to show you this. Look up how to use it somewhere. I made another YouTube video that talks about it, and it's in like the first minute or two, so you don't even have to listen to the whole thing. But you'll find this thing, and it says fluxes, and then like A, B, C, D, M, G, and V, and you're finding the flux magnitude in the V band for each on the website. So you get this from the data file, you get this from the website, Vizier Simbad, and you get this also from the data file. It's right next to the object, I believe. And you can plot these things out, and then you can get these numbers from the program which I'm going to show you how to run, which hopefully your professor gives you. And then you can compare the two. Okay, so I'm just going to scroll through the rest of this, and then you and I will get back to these weird numbers here, which seem to come out of nowhere. They come from here, and this is the command. Hopefully you're in a folder that has the Hermes etc Pi command in it, and you might need to, source the pipeline, or ML Anaconda or something to get this like Python up and running and working on your computer. But if you have Linux, it might just work automatically. Okay, so these numbers here come from this here. You have wavelength, and you have the electrons that are generated in the detector from a star with this magnitude. So wavelength and electrons. Come over here, wavelength and electrons. There we go. And then we're going to compare the wavelength and the theory electrons, which is this, to the wavelengths and the measured electrons, which come from the graphs. Yeah. So the plots, after the plots were plotted, I took the data at those points and put them here. So comparing these to those. Okay. That was the code, and there's 2 more programs you need to run on Linux or terminal or something, and you can find more information about how to run those in here. So maybe it's autumn 2020 and you're in Belgium and you like tables of contents. So abstract, introduction, classic, usual stuff. Here's a schematic of the Hermes, and you're going to get your Blaze wavelengths. Here are the commands, so if you want to copy it from some cloud in some network somewhere, then that was it up there. This is a useful command that you might be given to make a plot very simply, quick, and easy, though it seems to be weirdly focused on a wavelength that you can then after zoom out from. And here's your rainbow. So these are called orders: first order, second order, third order, fourth order. Actually, it might be transposed, so this might be the first order, second order. But I think they have to do with the sensitivity of the spectrograph to photons that have this wavelength. And so obviously, like here, it's very efficient and very sensitive, and then out here, it's not as good. And you'll do some math. You got to get Blaze wavelength, Blaze angle. Oh, sorry, yeah, find the peaks of all these. When you get the peaks of all those are the peaks. Where the peak is, that wavelength is called the Blaze wavelength. And then you get Blaze angle from the Blaze wavelength using this formula. And then you can compare the calculated values, which you just did from that formula, with the theoretical ones that you can look up in a source that hopefully somebody gives you, or it's in my references. And they match. And if you want to see how well they match, here's the difference over thousands of angstroms, and it's not very big, especially in these middle orders. And if you want to just do instead of magnitude or least squares kind of graph, just a differences graph, it's almost linear, which suggests there's a systematic error, not random error. A lot of math, and then I think, what are we on now? Resolution? Yeah, resolution. So the idea for resolution is you have this calibration from the thorium-argon neon lamp, and every one of these needles is actually not a needle, it's just a very narrow peak or hill, and a Gaussian distribution can model that hill, and then you can get the resolution by the full width half max of that distribution. I did not finish this in time, so here's an order. It's just one of the colors of the rainbows above, and I was able to find the peaks. However, and then I was kind of able to make a model over it. However, I made this model just by eyeballing the standard deviation of the model instead of running an optimization loop, which you should run an optimization loop. And then when I tried to do this over all peaks, or even just these 4 peaks, my for loop kept crashing, and I ran out of time. Sampling is kind of the same thing. And then spectral range is, I guess, these lines or something in between the peaks, or where they intersect. because if a photon comes in and it's on this line, then it can go into either. And if it goes into both or something, then you get like a double sampling, and you think that the star is emitting too many times the photons at that wavelength or something like that. Okay, stability. Oh, this is same plot, just zoomed in on the left, and same plot zoomed in on the right. Stability, you have to use this Hermes config file and copy or change the analysis results and where the debug is. And then, oh yeah, going back to free spectral range, you see that the black lines get further and further apart. So this is the distance between the black lines, and this is each next black line, and the distance gets further and further apart. Where was I? Okay, yeah, so you have this, make it your own, and then after that, you run the command, which is here. I hope you can zoom in or find it in the cookbook, and you should get these plots. They just come. They just get downloaded or installed or made into whatever directory you assigned them to go into. And then after that, yeah, there should be three, kind of one in the beginning of the night, one in the middle of the night, one at the end of the night. And you can see that, oh yeah, like it moved a little, right? This is, it's hard to see. It says kilometers per second. So 0.02 is 2 meters per second. And somewhere in the literature it says that, like, 1 is great, 5 is kind of, the gold standard, and so 2 is, less than 5 and wonderful. It's a stable night. And then the average or something's like 2.5, and here you go. Here's my average, or my night is exactly on par with the average. Find that in the references in the literature. Okay, efficiency. So however you want to define efficiency, that was that thing that I showed you earlier. So remember this? Yeah, this is efficiency. And this is the command you'll use, except this is the V magnitude of the star, and this is the exposure time, so those will change. Even though this looks funny, just leave it there, I guess. It never posed any problems for me. And your data will look like that, but, in your Linux format and with a different font, I'm sure. And you have a discussion. Oh, here's the efficiency. So, yeah, it kind of matched there, but then it, did not match there or there. And, your intensity, or your electrons that get generated from the photons that come in, should be really strong, I guess, measured, and wasn't very strong in theory. So, over 100% efficiency, right? Like, that's not realistic. Something weird happened. Or I'm doing it wrong. And if you have errors, you talk about them, like what you did wrong. And if you have future works, like how you might not do it wrong, you just write about those. And you have a conclusion, and there are your references. So definitely cite your sources. This is what happened when my for loop, when I made the for loop over the other peaks. I just haven't still to this day gotten the optimized Gaussian models to converge like they did in the example one. And yeah, so here's your free spectral range, how it starts out really small, 40 nanometers. Oh, I just didn't put the units, shame on me. And then, sorry, angstroms, and then gets larger as the spacing between each of the orders grows as you get to higher and higher wavelengths. I did get all the peak locations, but I did not get where their wavelengths were, since these get remapped instead of on wavelengths onto pixel order. And going from intensity to pixel is pretty easy, but then going from intensity to wavelength requires a lot more debugging, which I ran out of time to do. And those are the objects that my night observed. And then these are the efficiencies, theoretical efficiencies, of what you should get given the magnitude of that star here. So I wrote this for reference and clarity, but this is the output underneath of the Python script which you'll use, and so you have to make sure that this Python script matches the star that you look up on Sinbad or Bazier or something. And my night looked at 11 stars, so there should be 11 of these tables. And yeah, after you get your full width half max of all, 1,000 resolutions, you can plot them. Since I got one, but this should just be a massive scatter plot of 1,000 different resolutions. And Thorium-Argon neon missions, and you already saw my code, but you can use verbatim to copy and paste it in here. And you are definitely not finished with the project, but that only comes with the deadline in my experience. Best of luck to you.